Hi guys, so today we are doing the very last lesson in chapter 2, which is lesson 2.5. We are going to talk about all about inverses today. And then after Thanksgiving break, when we come back, we will do your chapter 2 review and then your test. Okay, so first thing we're going to do today is talk about how do we verify that two functions are inverses. We will also determine how to find the inverse of a function, look at the horizontal line test, and how we graph inverses. So lots of things with inverses. Okay, here is your warm-up for today. So as always, please go ahead and pause this video, try on your own, and then you guys can come back, unpause the video, and we'll go over the correct answers together. All right, so here, this is a review of composition of functions, which you guys have just learned. We are asked to find f of g of x here and g of f of x here. Remember this little O symbol represents the word of. So we can also rewrite this as f of g of x. So g of x, we're plugging inside of f of x, and then g of f of x, okay? So one thing that sometimes helps me is to underline or put a box around what function is going in within the other function and where it's being replaced. So I'm replacing the input in function f of x with this entire thing. So I would get, instead of x plus 4, I'd get this entire expression for g of x, so x minus 4, all of that plus 4 on the outside. That should be a plus sign. And then we simplify. So minus 4 plus 4 gives you 0, and we're just left with x. All right, and then opposite, so g of f of x, now we're taking function f of x, and we are replacing the input in g of x with that. So now we would get, instead of x, all of f of x, which is x plus 4, and then minus 4 on the outside. Okay, and then we simplify this. 4 minus 4 gives you 0, and we're also left with x here. So these both work out pretty nicely. Okay, so moving on to our definition of an inverse. This is our formal definition that you'd get from a college algebra book, and then I will explain it a little bit more. So it says, let f and g be two functions such that f of g of x equals x for every x in the domain of function g, and g of f of x equals x for every x in the domain of function f. So looking at this example that we just did in the warm-up, in essence, we are looking for this sort of thing, where when we plug one function into the other, we get x out both times. Okay, so an inverse function, the more informal definition, is a function that undoes another function. So it does the opposite and backwards of some sort of function. Okay, and if it undoes the other function, it does the opposite and backwards, it reverses everything that just happened. Then when you plug one function into another, you should be left with your original input that you plugged in, because everything else undoes what the original function did. So that is why when you plug one function within the other, you should just get x out both times. Okay, so that this means that if two functions are inverses, then f of g of x and g of f of x will always have to equal x. This is the key thing here. And this is how we verify that two equations are in fact inverses of each other, is we plug f of g of x and g of f of x in. We simplify those, and if they both equal x, then they are in fact inverses. One other important thing to note is that the notation that we use for inverse functions looks like this. F to the power of negative 1 of x, we read this as inverse of f of x. Okay, that's what that to the power of negative 1 means right there, but that's just the notation that we use to denote an inverse function. Okay, so let's actually practice verifying some inverse functions. So we've got f of x here and g of x. It says show that they are inverse functions using the definition of an inverse. What that means when it talks about the definition of an inverse is that we have to find f of g of x and g of f of x. So let's go ahead and do that. We'll start with f of g of x. So we're going to plug this in to function f here. Okay, so we get 4 times this whole thing minus 7. Sometimes I like to just put parentheses where the x should be and finish writing the rest of the equation first. That way I make sure I'm not leaving anything out. Okay, so then I'm going to plug in the x plus 7 over 4 from the g of x right there. and we're going to simplify. So this is the same thing as 4 over 1 times x plus 7 over 4. Well, if I multiply this, the 4 in this numerator is going to divide the 4 in this denominator, which is just going to leave me with x plus 7 minus 7. And then 7 minus 7 is going to give me 0, and that gives me x, which is what I'm looking for. However, you have to always try both ways. So even if you confirm that f of g of x is equal to x, I want you to also plug in g of f of x. The reason being is that it's easy to make mistakes. So if you make a mistake, you want to really be sure that you're going back to verify that it works both directions. Okay, so now we're plugging in f of x to function g. So we get parentheses plus 7, all of that divided by 4. I'm going to rewrite function f of x in this parentheses, so 4x minus 7. Okay, then we would simplify the numerator. So we could get rid of this parentheses. The negative 7 minus 7 is going to go away. Then we're left with 4x divided by 4, and then that simplifies to x. All right, so here we do verify that both f of g of x and g of f of x give us x, which means they are inverses, and that would be our final answer. Be very, very careful here though. Like I showed, I want you to make sure you're showing every single step to simplify. Some students will skip doing that and they'll just see, oh, I have a 7 and a negative 7 and a 4 and a 4, and then just try to start canceling things, which I don't like that word anyway, because we're not canceling anything. In math, we're just doing operations. We're adding or subtracting numbers that give us 0, or we're multiplying and dividing them to give us 1. Okay, so be really, really careful that you are writing out every single step to make sure that you're simplifying correctly. All right, let's do this next example. So now we're going to show that these new functions are inverses. We've got f of x equals cube root of x minus 1, and g of x equals x cubed plus 1. So let's plug in f of g of x first. Okay, I'm going to take g of x, plug that in here for f of x. So we're going to get the cube root of this entire thing minus 1. Okay, remember I'm replacing x with parentheses, so I put the x cubed plus 1 in here, and then I simplify. So first thing you've got to simplify is whatever's underneath the cube root symbol. So we can simplify this. The 1 minus 1 is going to go away, so then we're just left with cube root of x cubed. Cube root undoes x cubed, and then we're just left with x. Okay, so we verified it one direction, and now we need to go the other direction, so find g of f of x. So this time we're taking f of x and plugging it into function g right here. So we've got all of x cubed plus 1. Okay, and then we're going to plug in function f of x here, so we get the cube root of x minus 1. And then we simplify. So if you look, the cube root is going to undo this cubing, and then we're left with x minus 1 plus 1. Minus 1 plus 1 gives us 0, and so we are also left with x here. So they are therefore inverses. I will tell you, if they're inverses, it's usually going to work out pretty quickly and pretty easily. So you're not going to end up with something real messy. If it's not simplifying easily, they're probably not going to be inverses, but you do have to simplify as completely as possible to determine that, okay? If you do, let's say you get like a 2x here, okay, instead of just an x, then this automatically eliminates this from being inverses. So if you get anything other than x, even if I got a 2x for this and a 2x for this, it doesn't matter if they match, or if I got an, x plus 1 for one of them and an x plus 1 for the other one. Even if they are the same expression, if they're anything other than x, they are not inverses. So just be careful on that. Okay. So now let's actually talk about how do you find an inverse equation if you're just given the original equation. Here are the steps. I'm going to give you a minute to write them down. So the first thing that you're going to do is you're going to replace f of x with y. We know that y is another way that we rewrite f of x. That's just in function notation. Then you are going to switch x and y in the equation. Okay, then you'll solve for the new y value. And then the very last step is you just have to rewrite it in function notation. So you want to replace y at the very end with f inverse of x to denote the fact that you have found the inverse function. Okay, so example number 1 here. We are finding the inverse of f of x equals 2x plus 7, so let's go through these steps together. Okay, step number 1, we're going to rewrite f of x as y, so we get y equals 2x plus 7. Step number 2, we are going to interchange x, y. So we get x equals 2y plus 7. Okay, this technically is the inverse at this step, but we always like to rewrite equations in the form where we have y equals something. So we want to isolate y and get that by itself. So in order to get y by itself, first I would need to subtract 7 from both sides. So then I get x minus 7 equals 2 times y. Divide both sides by 2. And over here I get y equals x minus 7 divided by 2. Okay, so that's the inverse function. However, we don't want to leave this as a y. We want to actually write this in interval notation with the f inverse of x out in front. Okay, so we just replace that because this tells me that this is the inverse specifically of function f of x. So that's why it's helpful, because it determines that is the inverse function and of which original. All right, so that's it. Let's go ahead and practice one more time with this. Okay, so let's rewrite this with y. Next step is interchange or swap the x and the y. So we get x equals 3 minus y divided by 4. Okay, and then we've got to solve for y. So y is in the numerator here. So in order to solve for y, I would want to get rid of this denominator. So opposite of dividing by 4 is multiplying both sides by 4. Make sure you put the entire left side in parentheses. So then we get 4x equals 3 minus y. Okay, then we would want to subtract 3 from both sides. We'd get 4x minus 3 equals negative y. That's the same thing as negative 1 times y. So we want to divide everything by negative 1. Now, what that's going to do, if I divide by negative 1, that's going to switch all of the signs. So I'd be left with y equals negative 4x plus 3. Last but not least, rewrite this in the correct notation. Okay, so there we are. Now let's go ahead and move on to talking about graphs of inverse functions. So how are the graphs of inverses related? Well, the graph of an original function f and its inverse, f inverse, okay, they are reflections of each other over the line y equals x. So if I draw over here a little coordinate grid, the line y equals x is a line with slope 1. So if I compare this to y equals mx plus b, this slope is a 1, it's a 1x, and then the b value is 0. So it starts at 0, 0, and then goes up 1 over 1, up 1 over 1, up 1 over 1, down 1 over 1, etc. Okay, so what this looks like is it is the diagonal line that goes straight through the origin. And so also, it should make some logical sense because when finding the inverse here, we had to replace or switch out x and y, that when you are looking at the graph, it is reflected or flipped over the line y equals x, because we're now saying with an inverse that y becomes x and x becomes y. So it's always going to be reflected over that line, okay? And remember, a reflection is just like when you flip it over that line or if you were to fold it over that line. This also means, because we flip x and y, that the coordinates of the original function, if they're x comma y, then the coordinates of the inverse function are y comma x. So every single coordinate point on there has just the flipped x and y values, okay? Which makes it kind of easy for us. So let's look at this first example. You could obviously use a calculator to help you out here, or you can just plug in these values. So if we take a look these two functions. We're going to make a couple tables for them. Let's start with f of x equals 2x minus 3. That's the original. So if I plug in these values, let's start with plugging in -1 here. So plug in -1, I get 2 times -1 minus 3, which is -2 minus 3, which is -5. Let's plug that in. F of 0 would be 2 times 0 minus 3, which is 0 minus 3, which is -3. F of 1 would be 2 times 1 minus 3, which is 2 minus 3, which is -1. Okay, and then if you continue the pattern, you're also going to notice it's adding by 2 every time, adding by 2 every time. So this is going to give you 1, and that's going to give you 3. So if we know those values for the original, then the values for the inverse function, even if you don't have the equation, you don't have to find that if you're just graphing it. It's going to be all of these x and y values or x and y coordinates flip-flopped. So we'd have -5, -1, -3, -0, -1, -1, 1, 2, and 3, 3. So let's graph those and confirm that it actually does look like it's been reflected over the line y equals x. Okay, so we've got -1, -5 here, 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 and here. So this is the original. And whenever you're graphing, I want you to get in the habit of labeling which function that's for. Okay, and then let's graph the other one. All right. My line's not exactly straight there, but you can get the point. Label this. Okay. And if I look, this does in fact reflect perfectly over the line y equals x. So that's the line y equals x approximately. Okay. And this is just flipped over that line right there. So you can also kind of just look at it visually and see, yep, it's a reflection over the line y equals x. Okay. So now let's verify inverses using graphs. So this is a homework problem. Number 7b, it says show that functions f and g are inverse functions using a graphing utility. So graphing utility just means Desmos or a graphing calculator or an app if you have one. So I just plugged these two things into my graphing calculator. I'll show you in a second. So we have f of x equals x cubed, and we've got g of x equals cube root of x. So if we are verifying with a graph, then what we are going to do is we're going to make two tables. We can do that over to the side. So let's put f of x equals x cubed right here, make a table, and then we're going to do the same thing with g of x equals cube root of x, and make a table right here. Okay, so x, y, x, y. We can pick any values to plug in. We just at least have to have a couple points on here. And if we look at a graph first, I'm going to go to my graphing calculator app. I've got, if you see in the upper left corner, I've got these two equations plugged in. I'm just going to hit the graph button. And this is really, really zoomed out. But if I zoom in, you're going to see the blue graph right here is the equation f of x equals x cubed. Okay, so it's that backwards S shape. And then the red graph is the inverse, or what we think is the inverse, which is cube root of x. And so it's just been reflected is what it looks like over that line y equals x. So let's go ahead and draw this real fast. Okay, so if we go back here and we just plug in a couple of values, let's plug in, for instance, -3, -2, -1, 0, 1, 2, and 3. Okay, so if we plug these in, we'll get y equals, or f of x equals -3 cubed. Okay, -3 to the power of 3 is a -27. Then we get -2 cubed, which is a -8. Then -1 cubed is -1. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27. So we could then graph those, okay? All right, so here's the original f of x. I label that. And then if we plug in some values to cube root of x, so let's try plugging in the same values that we have over here in this table. So let's try plugging in cube root of negative 27. Well, cube root of negative 27 is negative 3. We want to confirm. We're verifying, so we don't know for sure. Cube root of negative 8 would be a negative 2. Cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. Cube root of 8 is 2. And cube root of 27 is 3. So these are, in fact, all switched. And we saw just by looking at the graph as well that they look like they've been reflected over the line y equals x. So 0, 0 here. Negative 1, negative 8, negative 2. And then over here, same thing. Okay, so this has just been reflected again over this line, y equals x. All right, so we did in fact verify that these are inverses. Okay, the horizontal line test, we're almost there. The horizontal line test is similar to a vertical line test, okay, except the difference is that now we're talking about horizontal lines, obviously, and dragging those across the graph. So this is a way to determine if a function has an inverse function. So a function has an inverse function if and only if no horizontal line intersects the graph at more than one point. So if you sweep a horizontal line across the graph, if you sweep it up and down the graph, and it only touches one point at a time, then there's going to be an inverse function, okay? Now, I say there's an inverse function for a very specific reason. I'll tell you in a second. So what this means is you'll draw a horizontal line, or like I said, imagine sweeping it down the graph, and if it touches more than one point, you know it will not have an inverse function. Every function has an inverse, but that inverse is not necessarily a function itself, okay? So every single function has an inverse, but the horizontal line test tells you whether the inverse is a function or whether it's not a function. So let's look at an example. Here we've got what looks like the graph of an absolute value function. If we use the horizontal line test to determine if the graph will have an inverse function specifically, what we would do is pretend to sweep a horizontal line across the graph, okay? We're looking to see if it touches more than one point at a time, which it does. So at the majority of the points on this function, it's going to touch 2 points at one time, which means it fails the vertical line test. Or not vertical, horizontal. Excuse me. Okay, so it fails the horizontal line test, which means it does not have an inverse function. It does have an inverse, but it does not have an inverse that's specifically a function. Now, if we were to draw this inverse graph, this is actually the line right here, y equals x. So if we were to reflect this over that line, here's what you would get. You would get this V-shaped graph, but now it's pointing to the side. And remember, definition of a function is that each input has only one output and it has to pass the vertical line test. This does not pass the vertical line test, which is why that is not a function, okay? So the horizontal line test tells us whether or not it will be a function when you take the inverse and when it's reflected over the line y equals x. Okay, example number 2. We're going to actually find the inverse here of this function, and then we will apply the horizontal line test to determine if the graph is going to have an inverse function. So notice here something interesting. I'll talk about it in a minute. It says f of x equals x squared plus 4 for the x values that are greater than or equal to 0. So we'll talk about what that means. Okay, first thing we'll do is let's find the inverse function. So we set the equation equal to y and set up f of x. Then we replace x with y. We switch those so we get x equals y squared plus 4. Then we solve for y, So subtract here. Okay, now we have y squared and we want just y. So to get just y by itself, we've got to square root both sides. Now be really, really careful because when you square root, you get two solutions, the positive and the negative value. Okay, so we get y equals plus or minus square root of x minus 4. And then we replace that with our inverse notation. So plus or minus square root of x minus 4. Okay, now it said at the top that this only works for when y is greater than or equal to 0. Well, if I were to graph this equation, this is a parabola, and it's been shifted up 4 units. Okay, you could verify this on a graphing calculator. So it looks like this. And then if I were to reflect that over the line y equals x, like so, it is now going to turn sideways, and it's going to look like this. Okay, it's actually two square root functions. It's the positive square root function, positive square root of x minus 4, and negative square root of x minus 4. So this is actually the first part. This is the positive part. And then the one that faces downward is the negative part. Because when you flip a parabola sideways, it actually does not pass the vertical line test. If you were to sweep a vertical line through it, that is not a function. So what does this mean? It means that it has an inverse, but the inverse is only a function for this specific domain of when x is greater than or equal to 0. So if I look at the original graph, it only is a function for this half of the parabola, okay? And that is because then when you get the inverse, we've got a square root function, and square root functions are super, super particular. If you plug in a negative to that square root function, or you get a negative at the end, when you simplify whatever you've plugged in, then you're going to get an undefined answer. And so this is why this is something to pay really, really close attention to if there is a specific domain that a function has an inverse for. Because like I said, in this case, if I were to try to draw this entire inverse here, this is not a function in and of itself. But if I just take the value that is greater than or equal to 0, so this part of it, that part of the function is going to be an inverse function. So that part, okay? So just note that and be really careful when you guys are trying to solve these types of problems. Okay, last thing that we're gonna do an example of for your homework is how to evaluate inverse functions. So here this says find f inverse of g inverse of -3. So if I want to rewrite this, this is f inverse of g inverse of -3, which looks real messy, okay? In other words, we are plugging in inverse of g of -3 into the inverse of function f. So the first thing that you'd want to do over to the side is you need to find both inverses. So let's find the inverse of f of x. So we'd have x equals 1/8 times y minus 3. I'm just going to skip that first step of rewriting it as y, and I've switched it to be x, and then I would solve for y. So I'd add 3, you get x plus 3 equals 1/8 times y. Now 1/8, the opposite of that is multiplying by 8. So if I multiply both sides by 8, then I get the inverse, which I'm going to rewrite over here. So y equals 8 times x plus 3. And then rewrite that using inverse notation. So I know I'm going a little bit quickly here, just so that you can see what that is. Okay, and then let's do the same thing with g of x. So replace the g of x with y, and then flip-flop the x and y. So we get x equals y cubed. Opposite of cubing is to cube root both sides. So we cube root both sides, and then we get y equals cube root of x. Okay, and then this is the same thing as inverse of g equals cube root of x. Okay, so here's what we do now that we know the inverse functions. First, we are going to find what is inside, the innermost thing. So g inverse of negative 3. So all I'm doing is I'm plugging negative 3 in for the inverse function here. Okay, so then I would plug that in. I would get the cube root of negative 3. Okay, and that likely is not going to be something nice and neat. You can go ahead, take a minute to plug that into your calculator. I'm going to do the same. It's approximately negative 1.44. Okay, and then I'm going to just leave it in this form for now. Then we plug that into the inverse of function f. So f inverse of this g inverse of negative 3 would become now 8 times all of that plus 3. Okay, so we could either plug it in like this, or we're going to have to approximate here, so we could plug it in as negative 1.44 approximately. Okay, and then that plus 3 gives us about 4.44, and then times 8 gives us approximately 35.54. Okay, now a lot of times it's going to work out a little bit more nicely than this, but in this specific instance, we end up with kind of a messy decimal. So all you have to do is start with doing the inside, okay, evaluating that, and then plugging that back in to the outside. All right, so that is all for today. You have homework on the lesson 2.5 PDF. So these homework pages, go ahead and write this down, and then you guys can ask your teacher for help.